Sorry about lab stuff last week. I tried to blow all the rain offshore, but even I don't have enough hot air to blow all that rain out to sea. Hopefully, if we can keep the hurricanes offshore, we will do the lab we should have done last week, this coming week. So, come to the dry lab, Berlin 233, have all your pre-labs ready, and we'll take the little solar collectors out, and we'll go do that. That one you will have to do a full-blown write-up for, just like the one that I showed you as the demo lab experiment. Okay, saturated water vapor and temperature curve. Guys, I know you've all had thermo, and I know that you were introduced to the steam tables, and you were shown the pressure, temperature, dome, and all that good stuff. And a bunch of you probably got really good grades on the exam, and a bunch of you still don't get it. So today is going to be a demonstration of what the heck was that stuff all about. Okay? So, what we're going to do is we're going to take warm tap water, put it in a little flask. I'm going to put it right here. We're going to put this in a vacuum chamber. Put my little temperature sensor right there. And I'm just going to put this saran wrap over the top, only to keep the splashing down. Okay, it's not holding any pressure in, it's not doing anything like that. It's just keeping my vacuum pump from sucking in a bunch of water that will cause rust. All right. And let's just watch what happens. There we go. Now you guys can all actually see what's going on. Put the lid on. Trying to get a good seal around the bottom, because that's what makes it really fun. Lid up, take a good seal. All right, magic time. Here we go. So I'm going to turn on this vacuum pump. I'm going to decompress this chamber. Help if I turn on the vacuum. Okay, so, random poll. Who thinks that is raging hot right now? I got one honest person. Anybody else? Hot, hot, vote for hot? Okay, that seems pretty reasonable. I mean, I just saw that stuff boil. Let the vacuum out. See if I can break the seal. All right, moment of truth. Here we go. No. I need to tell you, no second-degree burns. Honest to God truth. All right, and no, I am not like some superhuman superman. Guys, it got cold. Okay? Now let's do it with some data acquisition and watch what's going on. I know I'm a horrible instructor. I could just use a water, it wouldn't matter, but it's more fun to do it this way. If it's not fun, why bother doing it? Okay, so inside there I've got the little temperature sensor, the exact same one that you're going to use on your solar collector lab, and that we're going to use throughout this course. We'll put this back on. Spin it around, trying to get a good seal. Not horrible. Smearing the grease around. I should use proper vacuum grease, but Vaseline is what I had available this morning, and it works pretty good. All right, let's see if I can split the screen. In the background, I have a cool little temperature logger running that I wrote. Because, you know, that's what I do. I like running all my own stuff. Okay. So we're sitting at about 93 degrees F right now. Let's watch the temperature profile. We'll do it again. Uh-oh. Temperature's going down, guys. Anybody think that's just not right? Temperature's going down and down and down while it's boiling away. We'll let it go for a few minutes, but in general, folks, what do you think's going on here? Anybody got a thought, a guess? Okay, shoot.
As the pressure lowers, the boiling point lowers too, so the water's getting colder as the boiling point lowers.
You're definitely on the right track. Give it a shot.
Right, the same thing, but the boiling point is getting lower, but it's causing water to evaporate, and that evaporation is pulling the energy out of the water.
Ding, ding, ding. Exactly. So, as we lower the pressure, okay, once the ambient pressure is equal to the vapor pressure of the water, okay, so that water is going to have some certain vapor pressure at what used to be 93 degrees, now 81 degrees. Okay. If the pressure in the bell jar is lower than the saturated vapor pressure of that water, it boils. Okay. And that has some huge, huge implications in the world. Okay, so it's boiling. It's going through a phase change. And we all know that, you know, if you boil a pot of spaghetti on the stove, you got to put energy in to keep that water boiling. So the change in phase is endothermic. It's an energy absorbing process. I don't have any energy source other than the internal energy of that water. So as the phase change is trying to happen because the pressure is going down, it says there's only one place to suck that energy from. That's the internal energy, so the temperature goes down. And depending on how good my vacuum pump is and how many leaks I have in my system, the lower I pull a vacuum, the lower the temperature of that water. I have actually seen demonstrations of this where people have made ice just by sucking down pretty much almost a pure vacuum. So let's see, we're getting 76, 75. Let it go a few more minutes, see what we get down to. And then we'll go back to the pressure temperature curve and we'll see what the actual pressure is in that jar. So I always thought this was kind of a neat thing because if I had this all properly set up, you know, properly airtight, you could actually make a pretty nice refrigeration system just sucking on water. So this could be a decompressed heat exchanger. I put some water in. I got some water that's boiling off in there, and then cold water would come out the other side of the heat exchanger. You could do that. Not sure how energy efficient it would be, but you know, you can run the numbers and find out. Back in the 80s, we had this big to-do about, you know, causing ozone depletion due to refrigerants with fluorine. This gets completely around that. Kind of neat. If you're as geeky as I am. All right, we're still going down. I think if we let this go until in the end of class, you know, we probably hit about 60 degrees F, something like that. In fact, we'll just let it run. Come back over here. So if we look at the saturated vapor pressure line, so that means that if my temperature is about 77 F, then I must have about half a PSI of actual pressure. Okay, so there's no air in this anymore. This is all saturated vapor. And that's the key thing to remember. So I'm at about half a PSI, and I've probably got some tubing leaks. I've probably got some seal leaks. Okay. That pump could pull it down a lot further if I went troubleshot every last little joint. Okay, but that phenomenon I just showed you is hugely, hugely important. There's the rest of the saturated vapor line. Here it is on the table. So we just did this. So we just dropped from the liquid water part, the phase diagram. We lowered the pressure, we went right into steam, or in this case, saturated vapor. Cool, but so what? So one of the best applications of this, why this is important, is fighter jets. We have something called the Armstrong limit. It is the altitude at which the boiling point of water is 98.6 Fahrenheit, as in body temperature. So, somewhere around 60,000 to 63,000 feet, if I try going above that, there is no longer enough pressure to keep my blood from boiling. Okay, it's not just when I grade papers. Okay, it's actually at like 63,000 feet. So if you do not have a pressure suit above 63,000 feet, you will die. Because your blood will boil, you'll have embolisms in your arteries, and really bad things will happen quickly. Actually, you will be in trouble long before that. Even if you have enough oxygen in your suit and in your mask, you would not have enough pressure density to actually get enough oxygen into your lungs. The oxygen would be so thin, you just wouldn't get enough mass flow rate into your blood, and you would have passed out and died long before 63,000 if you were just, going up in a balloon or something like that. So you got to have a pressure suit. The other place this phenomenon is hugely important is ship's propellers and cavitation. So you can get into some regimes where your propeller is turning and you will actually move away from the water so fast and drop the pressure so fast on the backside of the blade that the water will boil. And then when you get back into the high pressure regime, those steam bubbles will collapse and they will slam into the surface of that propeller. And it can actually break off a bronze ship's propeller blade from cavitation. Okay? So you do not ever want to operate where your vapor pressure is lower than the ambient pressure. So let's see where our little experiment's at. This is going to be a short lecture today, guys. I know it's pretty started. So we're coming down, we're getting about somewhere around 69 Fahrenheit. But we're still boiling. So this lecture is actually going to be built on in the next lecture. So this one has saturated vapor in a vacuum, or solely saturated vapor. When you do your next lab, after the solar lab, what's going to happen is we're going to mix some air in there. We're going to talk about relative humidity and mixed gases. But we will hold off on that for another day. The last thing I want to go over with you guys that I didn't do in the last class, that's all I got for today's stuff, so let's just jump back a little bit. So back when we were talking about data streamer and programming, because this is not a programming class, okay, I made a list of every single Arduino command that I used when I wrote this course, and I put a list of them all right here under lesson 3. Let's see. We went through all of that. Additional commands. So this is all the stuff that I didn't cover last time. So pin mode. This would be up in the setup functions. So if you say pin mode 3 output, that sets pin 3 as either an output or an input. If it's an output, I can write a high or low to it, make it 0 or 5. If I make it an input, then I can read it. I can look at it and say, is that pin high or low? To actually make that happen, turn digital pin 4 off, you say digital write 4 low. And then if that pin is an output, 4 will go to 0. Or if you want to make it higher, you say digital write 4 comma high. Pretty simple stuff. If you want to put PWM, does everybody know what PWM is? I see you shaking no. No? Okay. So basically what it does is it takes the pin and it gives it a percent on time. So every millisecond, give or take, it will break up that 1 millisecond into sub-intervals. And if I say analog write 128, it will turn it on 50% of the time. So your average voltage becomes 2.5 volts. And you can input a number anywhere between 0 and 255. I'll go over that more. If that's shaky to some people, I'll put a slide together for next time we'll go over it. But it's just taking the average on time of a pin that's cycling. Okay, so current time equals millis, just how long the program's been running. You saw that in your template. Micros, just the number of microseconds the program's been running. Okay, I'm going to turn that pump off. But we're down to 67 Fahrenheit. And again, if I could pull that vacuum stronger, then the temperature would go right down to 32 degrees. And we could have ice in that flask. I heard some squealing in there, and I'm hoping I didn't pull a bunch of water into my pump, and now it's like metal on metal shaving stuff. That's the only reason I'm stopping it. Okay, so sensor value equals analog read 2. So that's going to return some value between 0 and 1023. And it's proportional to the voltage that it saw on the pin. So if you've got 0 for your sensor value, it means there's no value. It's at ground on the pin. If you see 1023, that was 5 volts. And you got to keep it within the range of 0 to 5. You can't put 12 volts on that analog pin without smoke curling out of it and bad things happening. Okay, this is a little bit more advanced. We're going to get into this when we get to our thrust-specific propulsion lab. Basically, you can take and access a memory location all at once. So on an 8-bit microcontroller, I can talk to all 8 bits. And it just so happens that port L is a memory location that has all of its bits attached to pins. So I can make it all either an output or an input. I can read it, I can write to it. If I make it all an output and I say port L equals 000, it turns everything off. If I were to make some of those zeros ones, it would turn the individual pins on and off. It's just a nice way to do things all at once. Or, instead of using this binary format over here, that's what the D means, I could just say port L equals 128, and it would turn pin 7 on. But I will go over that much more. That's kind of an advanced thing. If statements. Okay, this will mess with people. So the structure for an if statement in the C language, or the Arduino programming language, is if something in parentheses, in this case, digital read 4 double equals pi, then do some stuff after the curly Q brackets. Okay, so if whatever's in that bracket evaluates to true, then do the stuff. You can also do an else, as I showed down here. So if it evaluates to false, do other stuff. Did you guys see that's kind of structure in MATLAB, the if-else kind of idea. Okay. One thing that trips up everybody when we do Arduino programming is if you say if A equals 0, single equals, operative word, single equals, then do stuff. Okay, that is setting the value of A equal to 0. And it just does it, and it says, yep, I did it, true, true, A equals 0. And it always does the stuff in the curly Q brackets. Okay, do not fall for that one. That will just mess with your head. So if you want to say, if A equals 0, you got to do A equals double equals. That's the conditional. That's the testing one. But again, you won't need that. And interrupts, I'm going to have a whole class on interrupts. Basically, interrupts are a fancy way of doing timing stuff. When something happens, the microcontroller will drop everything it's doing and go service a particular routine. Where this is really cool is where you want to read encoders and get shaft speeds. Okay? Or maybe you want to watch for a propeller passing a laser. I can't imagine why you'd ever want to do that, other than we're going to have a lab one. All right. Guys, that's it. It was a short one for today. Free to go. Be sure to